Why is routing many photonic qubits on a chip difficult? Imagine trying to organize hundreds of tiny, delicate light particles to travel along specific paths inside a tiny circuit. It sounds simple, but in reality, it's quite a puzzle. Photonic qubits are quantum bits encoded in individual photons, which are great for carrying quantum information because they don't easily lose their state. But moving many of these photons through a chip is a big challenge. One main reason is that photons don't naturally interact with each other. Unlike electrons, which can bump into each other and create interactions, photons just pass through each other without much effect. This makes it hard to perform the two-qubit operations needed for quantum computing, like entangling to photons. Without these interactions, building complex quantum circuits becomes very tricky. Generating high-quality, identical photons is another challenge. Most current sources produce photons randomly, not on demand. This randomness makes it difficult to synchronize many photons traveling through the chip at the same time. Researchers are working on better sources, like quantum dots or atom-based emitters, but these are still complex and costly to develop. Photon loss is also a big issue. When photons travel through waveguides or optical components, they can be absorbed or scattered. Even tiny imperfections in the chip can cause photons to be lost. As you try to route more photons, the chances of losing some increase, which lowers the overall fidelity of the quantum operations. Routing photons involves precise optical switches and multiplexers. These devices direct photons along different paths for processing or measurement. They need to be very low loss and highly accurate. But current optical switches can introduce noise or loss, making it harder to keep the photon's quantum states intact. Entangling photons often relies on quantum interference and post-selection, which means many attempts are needed to succeed. This probabilistic process is inefficient for scaling up to many qubits. To build a large, reliable quantum computer, you need to perform many operations quickly and accurately, which is still a big hurdle. Fault-tolerant quantum computing requires real-time error correction and complex multiplexing systems. These systems need to work seamlessly to fix errors and keep the quantum information safe. Right now, integrating all these features into a photonic chip remains a major engineering challenge. In short, routing many photonic qubits on a chip is difficult because photons don't naturally interact, sources are probabilistic, losses increase with scale, and optical components are hard to perfect. But despite these hurdles, the potential of photonic qubits for long coherence times and room temperature operation keeps researchers motivated to find solutions. Advances in materials, nanotechnology, and new architectures are helping pave the way toward more scalable photonic quantum computers, even if it's still a work in progress.